So all of that has been talking about qualitative descriptions for the most part of solubility and concentration. We need to be able to specify concentration quantitatively in terms of numbers. And there's many, many different ways of expressing concentration. One of them is mass percent. And percent in general is the part over the whole times 100. So percent equals the part over the whole times 100. And for some people, if you can just remember that, you can figure a lot of this other stuff out, because you just ask yourself, okay, so there's this solution and they're talking about a percentage. Okay, what is the part and what is the whole? The part is going to be the solute, the thing that is dissolved in the liquid, the solvent. And the whole is the entire solution. So mass percent for a solution is going to equal the mass of the solute divided by the mass of the whole solution, which will be the mass of the solute plus the mass of the solvent. And what you have to watch out for in problems and questions using mass percent, sometimes they give you the mass of the solution, and sometimes they give you the mass of the solvent. And you have to recognize what you're dealing with. If they give you, this many grams of salt and this many grams of water, then you have to add those together to get the mass of the whole thing. So the denominator is the mass of solution, not the mass of solvent. And I guarantee you there will be a problem on the exam where I will try to trick you with that one. Okay, promise. So let's do an example. Calculate the mass percent of a sucrose solution containing 11.3 grams of sucrose and 412.1 milliliters of water. Assume that the density of water is 1.00 grams per milliliter. So mass percent. We say, okay, well, they want mass percent. What is mass percent? Well, mass percent is going to be grams of solute divided by grams of solution times 100. Well, what's the mass of the solute? What is the solute? There's two things here. There's water and sucrose. Which is the solute? Water's the solvent, so sucrose is the solute. Those two words are really similar. Solute, solvent, solution. So you have to listen carefully. So the grams of solute is 11.3, that was a bad 3, 11.3 grams. Now what's the mass of the solution? Well, they don't just flat out give that to us, do they? They don't even give us the grams, the mass of the solvent. They're giving us the volume in milliliters.
But water, milliliters is grams.
Water has a density of 1, and so you can just switch grams and milliliters for water. You can't do that for other things. But I'll show you how you would work that out if you wanted to do that. 412.1 milliliters times grams per milliliter, so this would be 1.00, the milliliters cancel out, and we end up with 412.1 grams. So for pure water at room, at a temperature where its density is 1, then the number of milliliters and the number of grams are equal. Is 412 the mass of the solution? No. So that's the solvent, but then there's also 11.3 grams of solute, and so you have to put both of them in there. And it's probably best to do that addition separately so that you don't screw up on your calculator. So 412.1 plus 11.3. So the denominator is 423.4. And then multiply by 100. And we're going to get 2.67%. 2.67% sucrose in this solution. Any questions? You can't have a percent concentration that's greater than 100. We did have that happen in percent yields, and we explained that that's because something went wrong, right? If you get a mass percent that's greater than 100, the thing that went wrong was your calculation. Because how can the mass of part of it be greater than the mass of the whole thing? It can't happen, except in Wyndham's world. There are other commonly used units, parts per million, parts per billion. We don't often hear this called parts per hundred, but parts per hundred is the same as percent. Percent means per hundred. Parts per million is how many grams per million grams. And parts per billion is grams per billion grams. And those can all be used as conversion factors. So if you have something that is, 5 parts per billion, well, 5 parts per billion means 5 grams of solute per billion. What is that, 10 to the 9? Yeah, per 10 to the 9 grams of solution. So all of those percent concentrations can be used as conversion factors.
Usually if they're at that high, so they're super dangerous.
And why do we have these different units? Why not just use percent all the time? Because sometimes you'd end up with 0.00000000005%. It's an awkward number. And so for something that's a really, really small concentration, like if you ever read the city water report that they send you every year, a lot of those things are measured in parts per million or parts per billion because it's a little teeny tiny amount. But sometimes that's all that it takes to make a bad something happen. I didn't plan that sentence out. So we can use mass percentages in calculations. So percent is parts per 100 parts. Grams of solute per 100 grams of solution. And so you need to be able to make your mass percent into this guy right here, and then bang, you have your conversion factor. There are other ways to solve these problems, but this is the one I'm going to teach. If you have a different way, you go ahead and use it. So how much sucrose in grams is contained in 355 milliliters, which is 12 ounces, of a soft drink containing 11.5% sucrose? Assume a density of 1.04 grams per milliliter. So this is one of those problems where it's just not, really obvious what we're supposed to be doing here. So we've got 355 milliliters. That's the whole soft drink, right? That's milliliters, that's the solution. And we've got 11.5% sucrose, which is the solute. 11.5% means 11.5 grams of sucrose per 100 grams of solution. Percent. 11.5%, 11.5 per 100. Per 100 grams of solution. So that's our conversion factor right there. We're trying to find grams of sucrose. Well, our conversion factor relates grams of solute and grams of solution, but they gave us milliliters. They gave us milliliters, but they gave us the density. So we can take the milliliters of solution and multiply multiply by the density. See, we want grams per milliliter so that our units work out. Dimensional analysis, it's 1.04 grams. So is it going to be really close? Yeah, but sometimes really close isn't good enough. Needs to be right on. 355 times 1.04. So 369.2 grams. And that has 3 sig figs. I'm just gonna, there's only the one tagging along there, so I'm just gonna leave in there. So that's our mass of solution. That's our given. So 369.2 grams of solution times, we want grams of solution on the bottom and grams of solute on top. So we get the units in there first, and then we put the numbers in. So solution is on the bottom, there was 100 grams of that. Solute's on the top. So we have 369.2 times 11.5 divided by 100. And now I'm going to round to 3 significant figures, and we're going to get 42.5 grams of sucrose. That's a lot of sugar. 42 grams of sugar in a can of soda. Any questions?